Thank you. Thank you very much all for coming. Thanks to the organizer for the invitation. It's always a pleasure to be in Barcelona, and I have really enjoyed the workshop so far. So you have heard quite a bit about diffusion and flow matching and stochastic interpolant, but I thought it might be useful that I give you, yet another perspective on them, and maybe trying to insist a little bit on what you can do with these tools that maybe go beyond what one can do with standard diffusion. So that's the aim of this talk, mostly. And at this point, it's becoming, joint work with many people. So I'm not going to list them all. They're over there. But I want to point out Michael Albergo, really, who was on the first paper, and Nick Boffi that joined in very early, and then Joan Bruna, because I'm going to present at the end of the talk, hopefully, if I have time, some result with him. We good? Yeah, okay. Okay, so the first few slides I'll go very quickly because you have seen that many times, so I don't want to bore you again with this. But so what are these? So there's this concept of stochastic interpolant that's also called flow matching. In fact, flow matching is more prevalent as a terminology these days. And it was also called rectified flow in three papers that appeared at the same time. And as you have heard many times now during the conference, the idea is to try to build a generative model by doing some interpolation first in sample space and building a transport that's associated with it. So the way you do the interpolation is using this interpolant here, where it's essentially a linear combination between data from a base distribution that could be anything, but for most of the talk I will take to be a Gaussian, and then data from your target distribution, and then you have this time-dependent coefficient here that are supposed to be smooth, time differentiable, and with boundary condition that guarantee that at time t equals 0, this gives you a sample of x0, and at time t equals 1, it gives you a sample of x1. Okay? A simple instantiation of this is just this interpolant, and the x0 and x1 could be coupled. There is no reason why they should be independent, but you could also take them independent, so drawn from the product measure between the base and the target. So by definition, as I just said, this guarantees that it interpolates from x0 to x1. Let me try to remove my... Yeah, okay. And I'll try to illustrate that very quickly in pictures. So imagine that this is, this is the base, this is the target, right? And then you have samples that are available from both of them. Typically, that's the only information you have about this distribution. Then you can construct this interpolant, which is essentially pairing points a priori at random if there is no coupling, okay, by a straight line if you use the interpolant that is linear like that. And then this, of course, induces a motion. So if this is how these samples that have been paired would move if around IT, if you vary t from 0 to 1 and 1 to 0 back and forth. And then in turn, this induces a motion of the law of this interpolant, which is of the measure itself, which is here depicted. Okay? And what you want to learn is the associated transport, so the vector field that realizes transport. And there was a little picture already like that, probably even better on the talk of a few days ago, where the idea is that you have this very simple result that says that you can realize the law of this interpolant via the solution of an ODE with initial condition from the base with a drift which is simply the conditional expectation of the time derivative of the interpolant taken at the condition on the interpolant going to a given point. So, in the picture that we saw, so this is here, you have, at this point, there's several rays here in red that are what the interpolant would be doing. You average them, and then you get the velocity field, okay? I can include the proof of this statement because it's so simple. It's essentially chain rule and the Tor property of conditional expectation, which is that if you look at what is the law of IT, by definition, it's the distribution which is such that if you take expectation against it, you get expectation over the interpolant. If you take the time derivative of this and you get chain rule, you use chain rule, you get this line. If you use the Tor property of the conditional expectation, you can replace that guy by its conditional expectation under the expectation. And then you can rewrite all of this as expectation over mu. And what appears here is this velocity field B, this conditional expectation. And what you have here is simply the transport equation in weak form whose characteristics is this. Okay, and that pretty much is the end of that story. Okay, so this now is a generative model through an ODE, because to sample the interpolant, you need to have data at both ends. But here, you only need data. Once you have learned B, you only need data at one end. So in particular, if you can sample the base, say a Gaussian, you can push this sample through the ODE to get sample at time t equal 1. So it's non-equilibrium transport from the target. Okay, and this actually is not a cartoon. This is actually what happens if you go in one dimension from a Gaussian to a Gaussian mixture with 3 wells. Okay, that's a little remark about, you heard about optimal transport. This is not optimal transport. It's an exact transportation, but it's not optimal transport. But you can prove a very simple bound that shows that you can bound the length of the path in W2, or the map if you wish, simply through an integral of the interpolant. So you can use that to actually control the length. So it's not optimal, but it can be made fairly close very cheaply. Okay, and then this you also have seen. Why is that useful in practice? Well, it's because you can use the L2 characterization of this conditional expectation. This thing is actually dying on me, so I don't know. Okay, I'll try. Okay, so which is that you can represent B as the argmin of this quadratic objective, which involves not only expectation over the interpolant, no longer conditional expectation. And so you can, what you can do now is that you can use all the toolbox of machine learning, meaning you can represent B in a rich parametric class, a deep neural network, a transformer, what you have at your disposal. And then this becomes a loss for the weights or the parameters that you have in this network, in this parametric representation. And well, then you do optimization using the standard toolbox, meaning by stochastic gradient descent. And all the results I'm going to present to you later are based on this. Okay? Now, this was transport with ODEs, but you can also create or build generative models that involve SDEs. And the reason is this little manipulation that also looks very simple, but it's in fact pretty profound, which is that the transport equation that I wrote to you on the previous slide can be rewritten as a forward Kolmogorov equation or a Fokker-Planck equation, meaning you can add some diffusion, provided that you compensate for it by a term in the drift that involves the score. Okay? And this transport equation is exactly the same as the one that I wrote before, because there is this little identity that says that if ST is the grain of the log of the distribution, then the grain of the log is the gradient divided by distribution, time distribution that gives you the gradient, and the divergence of the gradient is the Laplacian. And so that means that, in fact, this term here cancels exactly this one, if you have exact estimation. But this also means that now you can realize the generative model using a diffusion where the diffusion coefficient can be adjusted. In fact, it can be adjusted post-training. Okay, it can be taken, if you take it to 0, you go back to the ODE case. If not, well, you get the SDE. Okay, and then there's one more little result, which is that if you use Stein identity, which is this identity, and the fact that the conditional expectation, so the score, it can be expressed in this term, this is Stein or 3D, and then if you use the trivial relation on top of it that the expectation of IT at IT equals is X, you can solve this equation to express the score in terms of the drift. So there's only one thing that you need to estimate, is the drift, and if you have the drift, you have the score, and if you have the score, you can do sampling with SDEs. Okay, so if summarizing this, just so that we see again things in picture, the construction is that as follows, is that first you can choose an interpolant, and that defines a connection in distribution space, right? That, for example, the choice of the interpolant could give you that if you go from this 2-mode mixture to this 3-mode mixture, one choice of interpolant, you can't see that, but it's one choice of the coefficient alpha and beta, would give you this path. This another path is a third path. Once this is fixed, you have fixed the transport, you learn the drift that's associated with it, and you learn the score that's associated with it, and then you can sample any one of these connections with the associated generative model. So what you see below is that for every one of these row, there is no column that show you how you can sample. So this is what the path are, the density, all the density are evolving, and this is evolving them with the ODE, the SDE, or SDE with more noise. Okay, and this is to connect with what Stefan was saying. So if you simply take the ODE, right, and you start with one realization here of the Gaussian, then with the ODE you would always get, and this is something that has been trained on the data set, it's called the flower data set. So you would get that this generates this flower, and it will always generate this flower because it's a map from whatever initial condition here goes there. If you to have variability here, you would have to vary the initial condition here. You draw the x0 among different noises. But if you take the same guy here, but then you put noise on it, you can get the diversity of flower, and the diversity increases for conditional on this, given the value of the coefficient. Okay, and remarkably, as already pointed out by Stefan, there is something that arises here that kind of sort of magical, is that this actually does more than memorizing the data set. So for example, if you take this flower here, that is this one, you can actually try to go in the training data set and find what are the flowers that were the closest to it. If you had memorized, you would find this flower, but you don't, and the closest flower are these. And you see they have common features, but this is kind of a new flower. So it has really created, there's some generalization. We don't understand this very well. Okay, so that was my very quick summary of stochastic interpolant. You have seen that many times. And now, well, you can, this also has been said, you can generate actually pretty remarkable image with this type of formalism. This is something that was done in-house with Seiying Che, who is somebody in a Courant Institute that is a specialist in computer vision and knows how to compute, so you can do these things. But this is really not the technology that is being used in many of the image generators that you find on the web. And then it allows to do various things like you can do deblurring, denoising. You can do in painting like this, where you can use the formalism, the flexibility of the formalism to perform all of these tasks. Or and I'm not gonna, you can also do conditional generation, and then conditional generation with rollout, where what you use to generate, you use as a new condition, for example, to create movies. Okay, so these are, for example, images where you use movies, and what you try to do is conditional on a few of the previous frame. You predict the next frame, right? And then you use what you have predicted as new condition, and you keep rolling out. And so this way you can create artificial movies that have some diversity if you use the SDEs. And for example, what you see here are different generation of movies that are done with different rollouts, and they share only a few frames with the original one, but then afterwards here you see that they start to do things that are a little bit different while remaining reasonable. Okay. All right, I don't want to insist too much on this example because I want to focus on the theory. And so I'm going to do two things. First, I will make a connection with the existing methods now, and then I will show you how you can go beyond that. Okay, so first of all, let's go back to diffusion very quickly. So you have seen this figure now is pretty much, many talks are using it. It's from Song's blog. This was the original breakthrough, where what people, what they did is essentially, and this was following, work by Sasha Dixon and others, was that you take your data, you noise them by passing them, for example, through an SDE, and then, you can time reverse this SDE, provided that you learn the score, which allows you, instead of going from the noise from the data to the noise, to go from noise to data. Okay, and this was really the breakthrough, because
made, it created a connection in distribution space in a different way than interpolant, but I'll come to that in a minute. And then there was the realization, building on work by Eijnden and Vincent, that in fact this reduced then the problem to a quadratic regression of the score, which can be done fairly easily, which was the equivalent of learning the drift. Okay? Now, let me make the connection with the interpolant so that you see where this is coming from. Suppose that the way you go from data to the noise is through an Ocean and Beck process. And I'm using tau here as a different time just so that the connection becomes clear in a minute. So you can actually solve this equation explicitly using Duhamel principle. And the solution is actually telling you what? It's telling you that the data is fading out exponentially and is being exponentially replaced by a Gaussian noise. This is what you see along this. Okay? Now, in law, at any given value of tau, this term is equivalent to this term, where the factor z here is just a Gaussian random variable with standard, so n01. Okay? Now, realize that this process here takes data to noise in infinite time, and it goes from data to noise, but you can reverse time and compactify it by making this little transformation here. And then if you declare that this x of minus log t, so if you take, you declare this to be your interpolant, well, that's a stochastic interpolant. Okay? So you recover the formula of stochastic interpolant. So it looks we have not done much, but it's important to realize that conceptually, we have disentangled two operations that in score-based diffusion were sort of mixed together, even though they don't have to be. And these two operations is that on the one hand, you can build this connection, mu t, and to build it, you can use stochastic interpolant. That means you don't need to use diffusion. You can use whatever it is you want that actually brings sample from the base to the target. And then once you have done that, provided that this is time differentiable, then you can learn a drift and a score, and you can, as a result, sample it using either an OD or an SDE, with any diffusion coefficient that you want. You don't need to necessarily time reverse a diffusion. Okay? And in the second half of the talk, I will actually show you that we can use this flexibility at our advantage. That's the beyond diffusion. But before I do that, and very briefly, I will also make a link with maybe another method that is well known, which is called denoising. So if you think about the interpolant as being a noisy observation of the data that has been corrupted because you have added noise to it, okay? Then, the Stein estimator is telling you that the conditional expectation of the data given the information in the noisy sample has an expression that involves the score. And this can be used a priori to do denoising. But what people have realized for a long time is that if you do denoising like that in one step, it doesn't work very well. And so what was done in practice is to do denoising in multiple little steps. Okay? And then there is an interesting result that you can show is that there's a connection that you can make here, which is that if you do the Stein estimator where you go from a noisy sample with more noise to a noisy sample with less noise, there is a similar estimator that you can write down. It is written here that involves also the score. Okay? So you could iterate upon this, which is that you could denoise your sample in steps. If you do this, you don't have a generative model in the sense that I described, because this procedure will not produce samples that are unbiased samples from the target, just in the same way as this here doesn't produce an unbiased sample from the target. It's just a conditional mean that you are computing. Okay? But the remarkable fact is that if you put this if you do that on a grid, and you take the grid size to 0, you get back to the probability flow ODE. In other words, you can show the following thing, which is kind of simple, which is that if you look at this, you take this estimator here, you subtract the identity, you divide by the time step, what you get is precisely the drift. So what does that tell you is that there is a theoretical justification to this denoising by small steps, which is simply that if you denoise by small steps that are infinitesimal, in the limit, you get a generative model, which is precisely the normalizing flow that I was talking to you at the beginning. And from a numerical perspective, this means that this is sort of, you can think about this as an alternative discretization to the ODE, alternative to, for example, forward Earl or Runge-Kutta, which would, but okay. Okay, so that's that link. All right, so now what I want to do is I want to explain a little bit how you can leverage the formalism, okay, and start to do things that are a little bit, beyond what you can do with standard diffusion. And so I'll explain two things in steps. One is the choice of the interpolant. I told you can choose alpha and beta pretty much arbitrarily. Well, how can you choose them? That's one thing. And then the second thing that I'd like to describe is how to fix the diffusion coefficient, because I told you that you can take any diffusion coefficient, so which one should you use in practice? Okay, so I'll address these two issues. Okay, so let's start with the first. So first of all, there's a simple observation, is that when you do the interpolation here, I told you alpha and beta are scalar function of time, like 1 minus t and t. There is no reason to take them scalar function. They could be operator, matrices if you want, if you're working on RD. Okay? Why is that useful? Is because if you are allowed to take different choice of alpha and beta that are matrices, for example, you can start to do denoising in ways that are much more versatile than if you just put noise globally on your image. Right? Like for example, this is a denoising here that corresponds to removing, bands of pixels that there's supposed to be a movie, right? Where you go this way. This is doing it another way, and this is doing it in yet another way, where you have a patch. Okay? But then there's other thing that you can think about, which is like, for example, this here, this, Gaussian blurred image or Mercian blurred image can be thought of as some form of interpolant between this, and you can interpolate between these two states. Okay? So if you allow yourself to have alphas and betas that are more complicated function of times than just scalar function of time, you have a big there's many different tasks that can do. Okay. Now this per se is an interesting observation, but it still has a caveat, which is that if I just present it like this, then for every choice of alpha and beta that you have there, every parametrization there, right, you would need to relearn the score or the drift. But there's another observation that you can do, which is that, well, actually, you don't need to do that. You don't need to choose these guys beforehand, meaning before training. So let me explain this. What I mean is that you can now introduce what we call operator interpolant. I don't know if it's a good name, where formally it looks exactly identical to the formula that I had on the first slides, except that here alpha and beta are not viewed as function of time. They are just linear operators. And so you don't view the interpolant as a function of time. You view it as a function of these two operators. Okay? And if you choose these guys in different classes, you can a priori realize many processes like the one that they've shown you on the previous slides. Now, associated with this, you can introduce conditional expectation of the same type as before. Namely, you can, using the linearity here, you can introduce what we call multitask drift for a reason that will appear in a minute, where what you do is that you compute the conditional expectation of x0 or x1, where the conditioning now is put on this interpolant at a fixed value of alpha beta to be equal to x. So these becomes now a function of alpha, beta, and x instead of t and x. Okay? And because these are conditional expectation, well, you can learn them. Because you can, for example, for eta 0, you can again use the L2 characterization of the conditional expectation to represent this as the minimizer of a quadratic loss. The only thing that you need to do now here is that you also need to put some probability on your operators. Okay? Let me give you an example with a little bit of an abuse of notation. Suppose that beta is equal to 1 minus alpha, and suppose that it's diagonal. Okay? Then you can represent, you know, these products like Adama product. So vector, you know, I represent alpha here is the diagonal, right? So this is component-wise multiplication of these two vectors, right? And if you do this, this means that this is an interpolation where you can go from noise to data component by component independently in any order that you want, okay? And associated with this, if you want to go from the, you know, the noise to the data, well, you should be able to vary every component of alpha from 0 to 1 in a way independently. What does that mean? Well, that just means that as probability measure, you just, the nu that you put here on this alpha is just you say it's uniform on the hypercube. Okay, every component can take any value that you want. And then if you do that, you can a priori learn this drift. And then if you have learned these drifts, you have in a way a universal access to a universal generative model, because now a posteriori you can take any path in your operator space, and you can do generation along that ray or that path. So for example, if you take any path like this, right, the law of the interpolant along that path is the same as the law of the solution of this ODE. This again just chain rule. Whereas you need to be able to sample the initial value. So for example, this would be noise, okay? And then you can propagate. So if you wish, what this is a way of amortizing the learning on a variety of tasks. So you're making the learning more complicated from the get-go. But then once you have learned this more complicated object, you can do much more with it. Okay? And if you want to use SDEs, you can also use SDEs. Like there's no, you know, you can, again, use Stein estimator to express the score. So here's a few tasks that you can do. I'm going to start with these. And, you know, I understand that these are somehow, these results make me a little bit uneasy myself, like I have to tell you. But, okay, so here is something where what is done is that you take an image. Is either the cat or, you know, this face. And then what you do is that you can mask certain part that you choose and then unmask them. That corresponds to, you know, using this these alpha and beta, or alpha in this case, which is this Adama product, where you simply kind of noise only the pixels that are behind here the eyes. And then you can generate new eyes. And then you can do the same thing with the mouth, and then you can generate a new mouth. Okay? And this is all done without, I mean, to the extent that the learning has been done perfectly, this is all done without any approximation. There is no, you know, there is no bias that is introduced. You have learned this universal model that allows you to edit your image in the way you want a posteriori. Same thing with the cat. Here's another example that, you know, is maybe useful for robotic. Here the data is a very long trajectory of a walker in a maze, okay? And so you take pieces of this trajectory, you discretize them in time, and you learn a generative model that will create these pieces of a trajectory, but again, time slice by time slice, using again the Adama product. So if you do this, this means that at learning stage, you have just this long trajectory that goes in a maze in a way that you don't control. But at inference time, now you can say, well, I want the path to go from this point to this point, or from this point to that point by an intermediate, and you can vary the length, and there's all kinds of tasks that do that. And if you do that, well, you end up having these generative models that are uniform generative, again, universal generative model that allow you to do this, you know, this generation of paths that go through the maze from any point to any other point with any length by any intermediate. Okay, so it's okay. I might actually, this is a bit more technical, so I might maybe skip about this, but you can actually use this for posterior inference, which is that if you learn the drift for a distribution that you potentially don't know, let's say this target, but then you want to sample a distribution that is obtained from this one by tilting it using a reward function or a likelihood that you know. If this likelihood is quadratic, which is a restriction, then the drift that you have used, this multitask drift that you have learned here can be used to obtain, without any retraining, the drift that will allow you to sample this tilted distribution. Okay, and these are the formula that are there. For example, and this is related in a way to the model that Boyer discussed. You can actually do sampling of models where you change parameters, which is the tilt, and then you can learn to do it in one condition and then change the condition and get samplers that vary across conditions. So this is useful for fine tuning. I'm not going to discuss this too much because I feel it's a little bit too technical. Okay, next step is I want to discuss a little bit how to adjust the diffusion coefficient. Right now we have discussed a little bit how to adjust the alpha and beta. Now let's go back and say how can you adjust the diffusion coefficient? And first of all, why would you want to adjust the diffusion coefficient? Okay, so the reason is actually pretty simple. Is that I told you there was this little identity that said that I wrote at some point a Fokker-Planck equation like this, and I told you that this the solution of this Fokker-Planck equation was the same no matter what the value of epsilon, the diffusion coefficient. This relied on the identity that this guy here, S, was the score, meaning the gradient of the log of the distribution. In practice, you don't have access to that function. You need to learn it. That means that you are making approximation. The moment you are making approximation, when you vary epsilon, the solution of this equation changes. Okay? And so this means that the choice of epsilon here, given if beta hat and S hat are the score that you have and drift that you have learned, what you're going to get as a generative model, the result that you're going to get from a generative model will be affected by the choice of the epsilon because of estimation error. Okay? And so the question is, how can you, well, sort of optimize this? Like, how can you optimize the epsilon t, the noise, so the level of diffusion coefficient that you put, in such a way as to minimize the impact of the estimation error on the generation error? Okay, so let me explain this to you in a few slides. So first I need to give you a result which is of the same flavor as before. I use it because it's simpler to explain in this case. So this is a variant of interpolants in which the Bayes distribution, you could also play with the Bayes distribution. I have not described that here. This is one way to play. The Bayes distribution here is a point mass. It's a Dirac at 0. Okay? And the target is the target. And so there is an interpolant that you can build, which is this one, which is such that it allows you to sample from this point mass any target distribution. And you need to learn this drift, and then the score is expressed in terms of the drift in this way, and you get this diffusion coefficient here, where again, this diffusion, so this SDE, where sigma is the noise that you put in the interpolant, but then you can use a diffusion coefficient here, which is different from that guy in the diffusion. The simplest case would be to take epsilon t is equal to sigma t, then this guy disappears, but you can actually vary it. So you have a family of SDEs now. Okay? If these SDEs were exact, they all have the property that their law would be exactly the law of this interpolant. If you make any kind of estimation error, this statement is no longer true. So one thing that you can do is that you can look at the exact process. This is the one that involves the true drift and the true score, and the estimated one. And then you can, since if you use them with the same diffusion coefficient, you can use Girsanov formula to compute the path KL, so the relative entropy in trajectory space between the solution of these two equations. Okay? That gives you a measure of the error that you are making, of the generation error. It's not necessarily the measure that you would want. The measure that you would want is on the final time, t equal 1, but that's much more complicated because there you would need to solve a PDE, and you cannot do that. It gives a bound on that, but so this bounds, the KL at finite time, right? But so you can, you have this guy, and this quantity is a function or functional of the diffusion coefficient that you have put in. And so you can a priori think, well, if you want to minimize the impact of the estimation error on the generation error, you just need to minimize this object with everything being fixed over the diffusion coefficient. Okay? And I'm not going to give you the steps, but there is a remarkable thing that happened is that you can actually do this explicitly. there is a minimizer that you can identify that in fact depends only on the coefficient that you use in the interpolant, but doesn't depend in particular on the target distribution. And that's a remarkable fact. And this is this diffusion coefficient. Okay? So that's, and then there's another little remarkable fact that you can show, which is that you can actually give an interpretation to the result that you get, namely that the process that you get with this optimized diffusion coefficient is a former process with respect to some reference process. So let me try to explain what that is. Okay, so for those who don't know, so former process are a variant of Schrödinger process. Schrödinger process are an entropic regularization of optimal transport. Okay? In words, what is a former Schrödinger process is you are looking at the SDE that is the closest in KL from a reference SDE with the constraint that at time t equal 1, its solution sample a target. Okay, so your reference can sample anything, and the one that, you know, the Schrödinger bridge would be the one that is the closest to that one in KL, but sample the target that you desire. And this guy is exactly that. So the standard definition of formal processes is what I just said. So it's the, you know, it's the process that is the closing KL to a reference process but reach the right target distribution. And this gives you a different, and as far as we know, a new interpretation of this, which is just to say, well, you can also get them by requiring that you minimize from a more statistical standpoint, which is you minimize the impact of the estimation error on the generation error. Okay? Okay, so that was that for the, you know, the alpha and beta, and the choice of diffusion coefficient. Now I'm going to try to use a little bit, illustrate what you can do with this to go again a little bit beyond, you know, standard application. So, and I want to show you extension and scientific application. So the first one is actually, I'll go fairly quickly because I don't have much time. But because the first one is this: is that it has been mentioned in the previous talks that one of the problems that you have with this viewpoint, this new viewpoint on generative modeling, as opposed to former viewpoint, for example, that involve GANs, is that the learning has been made much easier because you have reduced it to a quadratic regression of the score or the drift. But inference is a little bit harder because now you need to do inference or generation, you need to solve an SDE or an ODE. And this is, you know, this is first of all involves some numerical error, but this can be controlled. But it can be costly because it could be that you need to take many steps. Okay, but there's a way around that, and you know, Song, I should put more reference here. Song and Elmon, who were the inventor of diffusion, have also been pushing this early on, and this is what they call consistency model. This is something that, you know, we term flow map matching, but it's in a variant, which is that you can, instead of, if you have an ODE, or in fact any ODE, you can associate to it a flow map. You can think about the flow map essentially as a two-time integrator of your SDE. It's the map which has the property that for any solution of this equation, if you take the solution at time s and you pass it through this map, evaluate at st, you get the solution at time t. Okay? So, I mean, there's a little picture here that kind of illustrates what it can be composed, it has a semi-group property, it can be reversed, and you can, you know, so if you have this guy, well, if you learn the flow map, you can actually do a generation in one or a few steps. You don't need to integrate that guy anymore. You can, in principle, just take this guy and, for example, take s equals 0 and t equals 1, and then, poof, you have one-step generation. Okay? What is remarkable is that you can also learn that guy. And so, you know, this is the novelty with Nick and Michael again, which is that you can, so first of all, because the map needs to have an identity property, so, you know, if s equal t, x of stx needs to be equal to x, you can always represent it in this way, right? And say that if you want to learn the map, you need to learn this two-time velocity. And then, well, you can just use properties of the map to actually write a loss that learn this velocity field directly from data. In other words, if you have learned this two-time velocity field as opposed to the one-time velocity field that we had before, now you can integrate your ODE in one step. Okay, and there are generalization of these to SDE. So there is little picture that explain a little bit what this is doing here, but let me glance, so it's not very important. The important point is simply that instead of having to learn the velocity field, you can learn the map, and then you can do generation in one step. And okay, so these starts to be, in some sense, there is something here which is there's kind of a no free lunch type theorem, which is that, of course, the map that is obtained as a composition of these original velocity field is a much more complicated object than the velocity field itself. Already the velocity field is a very complicated object because it's moving things in high dimension, but the map is like a monster. And so this leads to learning problems that are pretty heavy, okay? And there's a lot of engineering that is going on to try to do that in the most efficient way. We have done some attempt. This is not the best result, but this is just to show you that you can get reasonable images. So even on high-dimensional model, and there are in the literature no results that are appearing that are much better than this, by just doing one step. So these are images here that are generated by learning a map, where you take noise and it spits out the image in one step. Okay, and then this is if you increase the number of steps. Okay. This, a priori, is less costly than integrating the ODE or the SDE, with a little bit of a caveat, because it could be that the network that you need to use to learn these things is much more complicated. So one evaluation of the network of the map could be more costly than many evaluation of the network for the velocity. So typically when people compare, they try to compare apple with apple and orange with oranges, so they use similar architectures to do the calculation. So, but this is kind of an active area of research. I think it's an interesting one. Now with Jean, I'm doing okay with time, I think. So with Jean, we have done something else, which is like another generalization of this, which we think is pretty useful, which is a case where, so all of what we have done before were cases where we have data at both ends. Okay? And now for the remaining of the talk, I want to discuss cases where you may not have data at both ends. So the first case is this one, is that suppose that you have data that is corrupted data. They are coming, for example, from some experimental measurement. Okay, that's your data. You don't know what is the clean data, but let's imagine that you know the operator that has been used to corrupt this data. So you know what is the source of noise in your data. Okay, it's a reasonable assumption to make. There's many cases like that. Then, of course, you don't have your clean data. You only have the corrupted one. You cannot do the standard interpolant because you're missing the data at one end. But you can do something, which is that you can imagine that you have a generative model, and if you have a generative model, it should be able to take the corrupted data and turn it into clean data. Okay, so let's just write, so that means that you can sort of do a self-consistency loop where you can construct an interpolant that involves the corrupted data at one end and the clean data at the other end, but you don't know what the clean data is. So the way you get the clean data is you say, well, the clean data should be the result of my generative model at time t equals 0. Okay? Maybe there is a, did I put too many F's in here? Yeah, okay, so I typed this too quickly. So this should be just the clean data here, and the F should actually be there. I apologize for that. I could maybe write it, okay, I'll write it down afterwards. Well, maybe I should write it down now, because otherwise it's gonna be a mess. Sorry about this. So you take I of t, right? And so, what you would want to do really is that this is clean and this is corrupted. And then what you say is that for this, you take the result of the map, and for this, you take the result of the map that cleans the data passed to the corruption operator. So that's what I should have written there. My apologies. And then, then you close the loop, which is to say, what is that? This is a solution of this. And what is this? Well, that should be the conditional expectation of that. Okay? And that gives you consistent simulation, which is, we can prove, I don't show the term, that if they are satisfied, then that means that this is the map that, you know, that clean your data. Okay? And so you can solve these consistent simulation iteratively in a procedure that is a bit like expectation maximization, where you use the current map to clean your data, you corrupt it, you use this interpolant to relearn the velocity field, and then you loop upon this. And we can show under certain condition that this conversion, the fixed point of this procedure, means that you can clean your data. And in practice, on some example, it actually works. So I don't know if you're going to see this because they're a bit. So, you know, these are, what you see here is that these are original sort of images. Okay, these are the ones that are given to the procedure. So these are corrupted images, but we know the corruption. And then this is what the procedure is doing when it cleans these images. And this, for comparison, is what you would get from a generative model that you would train if you had the clean data. Okay, so it's kind of this is the benchmark. We can't do the baseline. We cannot do better than that. And this is a similar example with JPEG. So you know you take compressed image with a little bit of noise, and the idea is that you want to uncompress them by using this procedure instead of the standard one. And again, you don't see it very well, but it actually working reasonably well. Okay, so this is the part about self-consistency. Now, there's another instance where you don't have data, and I'm going to just end up with this very briefly, and this is Monte Carlo. We have heard from Monte Carlo from Jaume yesterday, right? So this, like, it's a universal method to sample distribution, but when you do Monte Carlo sampling, it's a very different mode of operation, modus operandi, than what you do with generative model, because here, typically, you have an oracle that allows you to, for example, evaluate point-wise. You can query the likelihood of your target distribution, which in standard generative model you can't. But you don't have any samples. That's the only information that you have. Okay, but so standard Monte Carlo procedure, they work in many cases quite well, but also in many cases they are plagued by slow conversions because most of the procedure generate sample from a proxy of the target distribution and then correct, either by doing metropolis hasting, which is constructive Markov chain, or by doing importance sampling, which is associated weights. And in general, the variance of the corresponding estimator that you get are pretty bad because your proxy is pretty bad. Okay? And so there is an idea that now is kind of sort of exploding also in the literature, which is to say, well, okay, there is a way a priori by which you could generate better samples is to use a generative model. Because if you have the perfect generative model, it should give you sample from the target by definition. And so the idea is to sort of try to do a feedback loop where you start with a Monte Carlo procedure, for example, and then you use this Monte Carlo procedure, which is a naive one, a vanilla one, to produce some samples, and then you use these samples to learn a generative model, and then you use the generative model to produce better sample, and you hope that this will converge and be give you estimator that work well. These are very hard problems, and fundamentally, probably without warm start, they will you can't discover by this procedure things that you really don't know, but there are certain cases where they work reasonably well. I want to insist on this because I think it's an interesting problem for mathematicians because, as I already said, this is a situation, so an application, that are very different in nature from the standard one of machine learning because, the previous one were unsupervised learning but with data. Here you have no data, right? The whole point is actually to create the data, and so that's both a curse and a blessing. It's a curse because you have no data, but it's a blessing because these are cases where since you have a model that allow you to assess the quality of the data, this is one case where you can have verifiable AI. In other words, you can test the quality of your model, which with images is much more complicated to do because we don't know at the end of the day what the distribution of images are. But here you do. Okay, so it's a nice area of research, and we have made there are several applications of this that we made. Now I want to conclude. Maybe with something that I said during the debate yesterday, which is kind of sort of the big elephant in the room here, which is these methods work remarkably well. The heuristic is that this method works remarkably well. It's a big mystery what they do, because there is something which is called the curse of dimensionality that tells you, what we are doing here is learning velocity field that map RD into RD with D that is in the million. Okay, these are monsters, right? And we know, since Bellman that in principle, meaning in the worst case scenario, this is not doable because of the curse of energy. You can't grid space in high dimension. This is what this says. Okay, this this is like for a bit of the undergraduate version, the 101 version of what curve domination is. But okay, so that, and so there is a big question as to why is it and how come that machine learning and these neural networks are actually capable of learning functions that are in high dimension. And it's clear. Right, that's the question. It's clear that, well, this is a fact. This is a fact of life. This is, there is no way to control. That means the worst case scenario won't work. But this means that in the problem that we have applied machine learning to so far, there is sufficient structure in the data that at the end of the day, there must be something that is intrinsically low dimensional that is actually being learned by the network, and they are very good at learning that. Okay, but what this structure is, we really don't know. And why they are so good at learning it, we don't really know either. Okay, so these are fantastic questions, I think, for mathematicians. And maybe my last slide is this one, which is that these questions are more than academic. Like, these days, this was also discussed in the debate yesterday, there's a bit sometimes a feel that people doing theory are a bit feeling, becoming irrelevant because there's so much advances that are being done, on the application side. And as I said yesterday, I think that these advances are fantastic and they are a big source of inspiration for new challenging problem. But they are really that. They are challenging problem that needs to be solved. These two graphs shows that. So this actually is the cost of AI in a way. This first graph is actually telling you or the quality of the model improve according to one measure. It's not very important what it is, as you increase the size of the data set. And the scaling is not good because this is logarithmic and this is linear. It means that you need an enormous amount of data to do improvement. That's not a good sign, right? So because you're going to run out of data very quickly. This one is a little bit more scary even, in a way. This is the compute that you need to do these to train these models. You don't know you don't see the scale, but I'm going to give them to you. This is this is in flops. This is 10 to the 12. This is 10 to the 26. Okay, and so what this graph and this is the early days. This is modern machine learning as it's being called. Like this is the early days of machine learning. Here we are in 2010. Right? And this graph here where you have Gemini is over there and this is what it costs to actually train these models, actually is showing you that the need of compute quadruple every year. Okay, so that's clearly not sustainable. I mean, in no possible way. This is way faster than Moore's law. Right? We know that Moore's law is over, but even if it wasn't, this would beat it by a big amount. So there is really a need to try to kind of design lean AI, and well, I don't know what mathematicians like yourself or physicists can do for that, but certainly they should be trying to participate to the effort because this is not going to go right. I mean, we're gonna burn the whole planet pretty quickly if we go on this way. Okay, and that's all I had for you today. You already seen the little shadow, but I'm going to put it anyway.